the new Linux offer coming with the SAMA5D3. As I discussed already this morning, so the SAMA5D3 introduced a new version of the Linux kernel. So now we moved to the Linux kernel 3.6.9, if I remember well. So basically, I will, as I already did this morning, I will do a short overview of our software ecosystem currently existing on the SAMA5D3. Then I will point out what are the new features coming with our Linux distribution around the SAMA5D3. I will give you more details about device tree. So I will also explain what is a device tree. This is a new feature coming with our Linux distribution. And then I will detail the SAMA5D3 booting procedure when using a Linux operating system. So you already saw this slide previously. So this is the different variants of the SAMA5D3. So some of them have the LCD controller in option, single or dual Ethernet controller, and all are pin-to-pin compatible. In terms of software offer and tools offer, so as you know, we provide the SAMA5D3 evaluation kit. Okay, so it's based on a motherboard, an LCD display board, and different CPU modules. By the way, we also have third parties who are developing and who provide their own CPU modules compatible with our evaluation kits. And this evaluation kit is coming preloaded with Linux and the Qt SDK based demo. In terms of operating system, we provide our free Linux distribution based on the kernel 3.6.9, and you will be able to retrieve it using our dedicated website, linuxforsam.org. So again, there is a user community, and there is also some guidelines and the different links to program the demo, to retrieve the different tools to getting started with development under Linux. We also provide for the first time the Qt Graphics SDK. So again, the demo we will see more in details later in my presentation is based on the Qt SDK. So it provides a set of widgets and so on. So on the free Atmel Qt SDK, you will have the software distribution, of course, the demo, documentation, and training material. I will come back on this in the next coming slide. Regarding Android, we updated a few days ago our dedicated website, androidforsam.org, with a new port. So a port based on Android 4.0, so ice cream sandwich, for those who are familiar with Android. So it works with the evaluation kit, of course, and it works with both standard LCD display and the Max Touch display provided by a third party. Okay. Another new offer coming with the SAMA5D3 is a GitHub repo. Okay, so GitHub is a versioning tool. So this is fully accessible to UFAs or even customers. I have the link, the internet link at the end of my presentation. So thanks to the GitHub repository, you will be able to follow up the development around Linux. Okay, so as you can see in this slide, you've got one branch for each software component. So for example, the 1891 Bootstrap, or U-Boot, or the kernel itself. Okay, so if you browse the GitHub repo, you will be able to see the different tags made by the Atmel software team, to which tag what was fixed, what feature was added or improved, and so on. So this is a good way to have up-to-date information regarding Linux software development. As you can see in this slide, I don't know if everybody can see this. So there is a branch which is called Barebox. So what is Barebox? Barebox is a second-level bootloader which basically inherits from the best of U-boot, but it has a smaller size and is also faster to execute. So in the next coming months, I would say, we will be able to have U-boot and Barebox offer as a third-level bootloader. Okay, so for now, there is no stable version working on the SAMA5D3, but it's coming. Okay. Now let's move on to the home automation demo. As I said in introduction, this demo is based on the Qt SDK. So this is basically a widget library. This demo was developed by our partner Timesys. Okay, so as you can see, this is mainly a nice graphical user interface. You've got an on-screen keyboard, lightning control, thermostat control, and a video player. Okay. One of the purpose of the hands-on of the two-day session is to customize this demo. So nice tips to remind when you go in front of the customer if you want to customize this demo to fit with customer expectations. Another nice feature which is implemented in this demo is the camera support. So if you plug a camera on the USB port, you will be able to display the pictures captured by the camera. Okay. Again, this demo can be retrieved for free on our website and also on Timesys website. So you can retrieve the binaries and also the source code. Few words regarding the Qt story. I will not be very long on this. So this is a toolkit based on the C++ language running on a lot of platforms such as Linux, Windows, embedded Linux, Mac OS, and so on. So Qt is licensed under two different licenses, a commercial, mostly used if you plan to extend Qt and sell it, or an LGPL license. The demo coming with the SAMA5D3 evaluation kit is based on the version 4.8, but the latest version is the 4.0, and it's also, and as I said, available under Windows, Linux, embedded Linux, and so on. So the recent improvements are related to graphic customization. So this is what is called Qt Quick. Okay, so using QML language and QML files, you will be able to customize the demo. And also the recent addition include Qt Mobility, the multi-touch capability, so related to touchscreen, and target form factor simulator. So it's for cell phones. What is Qt SDK? Well, mainly Qt SDK is based on three different components, I would say. So first of all, Qt SDK provides the GCC cross toolchain. Qt SDK also provides the different Linux software components, so the bootloader, the Linux kernel, and all the system libraries. Okay. And Qt SDK is, of course, also a set of APIs, so libraries, headers, different modules, and QML files for designing the user interface. So this is a complete cross-development environment, which has been ported to the SAMA5D3 family. Again, how to access it? As I said previously, the download is available for free on Linux for SAM, the dedicated website from Atmel for Linux environment. And it's also available for download for free from Timesys Linux link. So it's based on build and on a build root today, but we are currently working on porting it in Yocto. This is becoming a more and more popular distribution. So there is a work in progress to have Qt SDK ported on the Yocto distribution. What can you do with the Linux, the Qt SDK? So the Qt SDK is intended for Linux host machine only. This is quite important to remind. So basically, customer can use the software, the existing software or existing widgets as a starting point to develop his own graphical interface. And it also supports command line development for a Qt application, web application, or any embedded software. So that's it for the Qt SDK. Now let's talk about more in details about the Linux kernel. So as I said, we moved our Linux distribution to version 3.6.9. So before Linux 3.x, let's say, PowerPC and ARM architecture were very different. So PowerPC relies on device tree to describe hardware components and hardware details, but it was not the case for ARM architecture. It only relied to the source code. Okay, so it was two different approach regarding the software architecture. So thanks to the Linux kernel version 3.x, this architecture has been unified. So now for ARM architecture, we also use device tree architecture. I will explain what is the device tree architecture. Okay, so basically, the device tree is a tree-like data structure which describes hardware, and this is important to remind. Okay, so device tree only relies on the hardware and not on the software. In fact, a device tree is a set of different nodes. Okay, so what is a node? A node can be a peripheral. So, for example, if you browse the source code, you will see that let's say the reset controller is a node. But you can also have child node. So a node can have different children. For example, if you use an E2PROM, you can have one node for each partition. Okay, so this really relies on the hardware configuration. And why we are using the device tree structure? This structure allows to extract the hardware configuration from the kernel, which means that you will be able to run the exact same kernel on different platforms. So if you move your kernel from one platform to another, you will not have to modify the kernel itself. You will just need to create a new device tree corresponding to the new platform. So this is very useful if you want to accelerate the time to market for a new platform, and this also is the software migration. Okay. So this slide just shows what I told previously. What are the benefits of the device tree? So as I said, it decouples the kernel code and the system-on-chip data. So it will be easier to add the support for a new platform. You just need to modify the device tree to support a new platform, and there is no need to change the kernel source code. Okay. As a consequence, and as I said previously, port the existing software on a new platform is a lot faster. So how to add the device tree to an existing Linux kernel? Okay, so you first have to pass the board information to the kernel. So basically, you have to start with a new DT. Well, so DT stands for device tree. So you have to start with a new DT-enabled board file. I will detail in the next coming slide what are the different files to create. Okay, for the device tree, you have to enable the device tree support in the existing board files and also in the Linux kernel. Okay. So the different files used by the device tree are DTSI and DTS files. So DTSI stands for device tree source include. So this is a header file, as you can understand. And DTS file stands for device tree source. Okay, and it's located under the DTS into the Linux kernel. Another quite important information I forgot previously is that when compiling a device tree, we use a different compiler. This is a different tool used to compile the device tree, and this is also a different binary generated when compiling a new device tree. The last two steps to add the device tree support is to enable the device tree support for system peripherals and for peripheral drivers. So now, in the next coming slides, I would like to share with you the implementation we make of the device tree for the SAMA5D3. Okay, so the DTS file for the kit, for a given kit, will when compiling it, you will be able to generate an executable file. And as you can see in this slide, the file generated is a DTB file. So a device tree binary or device tree blob. This is the two terms used to name a compiled or an executable file. Okay, so the device tree implementation we made takes into account the different hardware modules, because as you already know, on the different variants of the SAMA5D3, you have a different set of peripherals. So for example, on some variant, you don't have an LCD controller or only one Ethernet port, for example. So you have to take into account those differences when implementing a device tree for the SAMA5D3. So it's up to the customer to enable each peripheral at its device tree level. By default, it's disabled. Okay. So last point on this slide, thanks to the overlay feature, specific DTSI files are created and are included into the final evaluation kit DTS file. Okay. So we have a device tree for the SAMA5 series. So SAMA5D3.DDSI describes the overall architecture of the product. So the buses, some information about the CPU and the embedded peripherals available or not in the whole series. Okay. And as I said, all the embedded peripherals are described as nodes according to the peripheral mapping and the implementation of the product. And again, as I said in the previous slide, all the embedded peripheral nodes are disabled by default, so it's up to the user or to the developer to enable it in his own DTS file. Okay, but by default, it's disabled. So that's the main information regarding the SAMA5D3.dtsi file. But of course, we have a DTSI file for each CPU module. So the device tree file also include some file dedicated for the CPU modules. This file describes the hardware architecture of the corresponding CPU module. So for example, information regarding the frequency value of the external crystal, information about the NAND flash, the LED support, and so on. So we have a file dedicated for the chip module. We also have a DTSI file for the motherboard, so SAMA5D3 So this device tree includes the different chip module DTSI files, and it describes the hardware implementation of the different external components which are connected to the SAMA5D3, such as the CAN port, the Ethernet port, and so on. And finally, the DTS file includes the DTSI file of the motherboard, if available, the DTSI file of the display module, and thanks to the overlay feature, you have the main DTSI file which overrides the correct machine model support and set the peripherals depending if it's available or not. So this is how we implemented the device tree from the SAMA5D3 evaluation kit. So let's have an overview of the different Linux components and functions available. So it's quite similar to the previous offer we had on, for example, SAM9 products. So you still have the ROM code, of course, the bootstrap, U-boot, the kernel, and the root file system. But now you have the DTB file, so the binary or the device tree blob file, to pass the low-level hardware information to from U-boot to the kernel. Okay, so the DTB file is used to give the hardware information from U-boot to the kernel. So let's see how to pass the information from the device tree into the kernel. So basically, you need to use the boot command, so boot cmd command. So you will have to, when using this command, you will have to provide the link address of the device tree and the link address of the kernel. So to finish with this presentation, so this is the standard example of the NAND flash boot. Okay, so basically, user will have to load the different software components in NAND flash. So first of all, the bootstrap, then the third level bootloader, which is U-boot, the device tree blob, SAMA5D3x ek.dtb, okay, the kernel, and the root file system. Okay. Once the application is started, the NAND flash boot, which is stored in ROM, will copy the bootstrap from NAND flash to SRAM, then execute it. After that, the bootstrap will copy U-boot in DDRAM and execute it. U-boot will copy the DTB and the DTB file and the kernel in DRAM2 and will execute it. Okay, so this is the standard non-flash boot process. So the last slide of my presentation is gives you some useful links. So Linux for SAM again allows to retrieve the demos and the source code of our Linux distribution, our demo, and useful links to getting started with developing under Linux. You got a similar website for Android for SAM. Okay, the TimesYs website to retrieve, for example, the Qt SDK, and you also have the address of the Linux for SAM GitHub in order to follow up the software development of our Linux BSP. Do you have any question? Okay. So I think we are done with the presentation today.